Hello, my name is Sebastian Falkensteiner, and I am presenting you the talk Puiseux series solutions of autonomous ordinary differential equations. Let's go to the maple file. As you can see here, it's a joint work with Francois, Boulier, José, Cano, and Rafael, Sendra. And we have already published a lot of theoretical results to this topic. And now we are currently working on implementing all these things. So for this conference, we have chosen to show you with some examples our theory and give you a short overview on this topic. Since we are working on the package, we will publish the package, a maple package soon, but currently the implementations are not good enough for a publication. Okay, let's go ahead. So the terminology, the title of the talk is Puiseux series solutions of autonomous AODEs. And AODEs means algebraic ordinary differential equation. Autonomous or constant coefficients means that the independent variable does not explicitly occur. The order of an equation is the highest derivative occurring in the differential equation. So let's go to this differential equation f1. As you can see, there are a lot of squares and other powers and products involved. So it's obviously not linear. And as you can see here, it's perfectly known to Maple how to handle this differential equation. And if you want to manipulate things, then you should use the package differential algebra. The example here is a first order. Now we want to look for Puiseux series solutions. Puiseux series are power series in one variable expanded around some expansion point. We stick to 0 or infinity because we handle autonomous differential equations, which means that we can shift the expansion point later. And in the exponents, the denominator is bounded. There are only finitely many terms with negative exponents. In the case where the expansion point is infinity, there are only finitely many positive exponents involved. Another important definition is the ramification index. So it's the least common multiple of the denominators and the exponent. So let's go to some examples. If we have this series here, which is the root of the sinus, then we have a ramification index of 2. In the other two examples, the ramification is equals to 1, but here we have the -1 as the lowest order term. And here is another example, which is quite famous. One may note that the computations with such series, so the series is a maple type, they are already built in. But for formal power series with non-negative integer exponents, the computations can alternatively be achieved by using the package power series. This is also a well-known package. Okay, and as I already said, we are now interested in formal Puiseux series solutions of autonomous AODEs or even systems. We will come to the systems later. Which method do we use? So in all our reasonings, we are using an algebro-geometric approach. This is perfectly described in the references. for now, for illustration, let us consider one given equation of order 1 given by f equals to 0, and we want to find solutions expanded around 0. Okay, first we want to compute a local parametrization of the curve implicitly defined by the differential equation. For this, one can use the alg curves Puiseux command. Okay, so for example, if we take the equation from above, we can plot it here so you can get an impression of how the implicitly defined curve looks like. Then we can compute the local parametrizations. So these are the parametrizations of this point 0, 1. Each of these local parametrizations define one of the curve branches. Okay. So for example, if we take the first of this, the first local parametrization of this parametrizations, then we get this branch here. Now it's good to know that a curve branch is defined by an equivalence class of local parametrizations. So if you substitute with formal power series of order 1, you get geometrically the same object. This is perfectly shown here when we substitute with this formal power series here. Now we plot the new curve in blue, and as you can see, locally it's exactly the same, and also globally it behaves very similar. So here we truncate because the behavior on the left is not good anymore. Okay, we are interested in formal Puiseux series solutions of differential equations, and it's rather easy to show that a solution defines local parametrization by raising the parameter to the power of the ramification index. So basically, we do not look for the solutions, we look for these local parametrizations instead. Okay, but how can we decide whether a curve branch corresponds to a solution, or if there is in this equivalence class a solution parametrization? Okay, first we can derive some necessary conditions. So if we have a local parametrization which is a solution, then as you can see, the second component is the derivative of the first component, and hence we can get easily a relation between the orders of these two components. Since the order of the components remains the same after reparametrization, this is a necessary condition. In fact, for one equation and an expansion around 0, this is already a sufficient condition. We will come to this later. So first, we check whether this necessary condition is fulfilled. In our case, from the curve above, the necessary condition is fulfilled since the derivative, the order of the derivative minus of the first component minus the second component plus 1 is greater than 0. In fact, this already determines the ramification index of the solution. In our case, this is equals to 2. Now we solve an associated differential equation coming from this parametrization, because if you compute a local parametrization, usually you do not compute directly this solution parametrization. You have another element in this equivalence class. computed. And now we want to compute this solution parameterization. Okay, for this purpose, we need to solve this differential equation, as already said, and we are doing this by simply coefficient comparison. In the theory, we know a little bit more, and we can directly compute the coefficients and can avoid this solve commands used here. Okay, let's go ahead. So we make an ansatz of unknown coefficients and simply plug it into the differential equation. Here you can see that we get a lot of restrictions on the coefficients. So here we have S1, S2, and so on. Moreover, for S1, we have this quadratic relation. And for S2, S3, and so on, it's S4 here, it's linear in this coefficient. So, as I already said, we know a little bit more than this, and it's always the case. So we also know which field extensions have to be performed. So there's one algebraic field extension for S1, the others are just given linearly, so there's no field extension necessary anymore afterwards. Okay, so let's compute this by the solve command here. And now, after having computed this reparametrization, we can directly compute the solutions. So we take the first component of the local parametrization, plug the reparametrization in it, and then raise the x to the 1 over n. N is the ramification index. Okay, so let's do this with what we have computed here. Okay, it's a rather long solution, so we have truncated with x to the power 7 here. And now let's check whether this is indeed a solution. As you can see, the first coefficients are all vanishing. Hence, it's a truncated solution. From theory, we also know how many terms we have to compute, from which on we can guarantee existence and uniqueness of the solutions. Also, we have shown that all the solutions are convergent. So this is often very useful and in practice, because we can compute more and more terms, and there won't be any new behavior of the solution. Okay, as I already said, we have implemented it in a Maple package, and I will use this package now for computing all the solutions. All solutions means that we compute a generic solution with a free parameter and some particular solutions where this generic solution may not cover the particular solutions. So if we compute all solutions from above, first we start with the solutions with the initial value y0 equals to 0. As you can see, the solution already computed is not the only one, and the other branches also define solutions. But these two solutions here have ramification index 1, whereas the other solutions have ramification index of 2. For this example, it would be too much to print all solutions here. So we also compute the solutions of an easier example. So print it here. And then we compute all solutions. As you can see, we have two generic solutions and two particular solutions which are not covered. Okay, as I already said, we also handle systems of differential equations. but not arbitrary systems, only those which implicitly define in space curve or the union of space curves and points. So for example, if we have given this system here, system 1, and the geometric version of it, let's plot it. So here we have a space curve, or basically it's the union of space curves and points. Then we can compute a reduced differential equation or more reduced differential equations of this system. But it's important to know that this system, the reduced differential equation, is of order 1 and autonomous as before. And it has the same non-constant form of Puiseux series solutions as their original system. This reduction can be done via the Rosenfeld-Gröbner command in Maple. So this command covers the regular chains and pseudo-remainder process we are using. In our theory, we show more that it is easier to compute this reduced differential equations than such rather complicated commands and methods. But for now, it's sufficient to do this. So the reduced differential equation of the system above, maybe let's recall it. So here we have given the system one variable and the order is 2. Here is the highest occurring derivative. And now we have the order equals to 1. And the reduced differential equation can be solved as before. So if we compute the solutions of this reduced differential equation with the initial value that y of 0 is equals to 0, we get these two solutions. And they can be read off almost directly. Okay, as I already said, we have also implemented a Maple package for the case of systems in one indeterminate. Let's do the same computations as before with this package. As you can see, we derived the same solution. It's also worth to mention that the reduced differential equation might be an algebraic equation. In this case, the system has only constant solutions. So for example, if we consider this system, the reduced differential equation is only y of x equals to 0. Now, if we compute all solutions of this system, we see that only the 0 is a solution. It is planned to also do a Maple package for the case of systems in several differential indeterminates, because here we already have theoretical results. But for this, we need to compute algebraic solutions only and do computations with them. Since this needs a new package already for the case of order 1, it will need some more time and investigation also in the computational part in order to be able to publish such a package. Okay, thank you for the attention and I'm looking forward to your questions.